So why do we use binary numbers in a computer? Let's take a look at that. So computers use binary numbers basically because it's easy to build circuits. So in a computer you have some voltage. Today it's around 1 volt is a 1 and around 0 volts is a 0. In the past it was 3.3 volts or 5 volts or even 12 volts if you go back far enough to be a 1. It's easy to build complex circuits with these. We use them as switches to switch whether 1 or 0 gets passed around. And that's how we design circuits today. Now, one other thing you could do is you could use multiple voltage levels. So instead of just having 1 volt be 1 and 0 volts be 0, we could say, well, let's have 1 volt be 1, 2 volts be 2, 3 volts be 3, this multiple voltage level logic. But there's a problem with that, and there's a very good reason why people don't do that today. And that's because the noise would kill you. And we'll take a look at that in just a minute. So digital logic is noise tolerant because it doesn't use multiple voltages to represent multiple values. It just has 2, 1 and 0. So values that are close to 0, we say are 0, and values that are close to 1, we say are 1. And this means that if noise comes in and pushes things off a little bit one way or the other, we still say it's a 1 or a 0. So for example here, if I have no noise, I can do 1 plus 0 and I'll get 1. But if a little bit of noise comes in, say that 1 gets pushed down to 0.9 volts, and that 0 gets pushed up to 0.4 volts, well, the logic is still going to interpret this as a 1, and that is a 0, so we'll get 1 out the other end and not 1.3. Analog circuits don't work that way. That's why we use digital circuits. Analog circuits, if I have 1.4 plus 3.4 volts, I'm going to get 4.8 volts. So even though these have been pushed off a little bit, it's going to give me a result which isn't what I wanted. So let's take a look at how this actually works. So here we're going to look at the inputs to a digital circuit. So it goes from 0 volts up to 1 volt. We're going to compare that to how the digital circuit interprets the value from a 0 volts to a 1 volt. So what's the output going to be from the digital circuit? It's going to be a 0 or 1 or somewhere in between. And we see that this is what the transfer function looks like. So for this range in here, for any input in this range, the digital circuit is going to interpret as a 0 and it's going to output 0 volts. Now, somewhere in the middle, something bad's going to happen, but beyond that region, anything over here it's going to interpret as a 1. So any value that's input in this region, it's going to interpret as a 1, and the logic's going to process it as a full 1. So what this graph shows you here is that as long as my noise just pushes me around in this region, or this region, the digital circuit will still interpret the value correctly. If it pushes me into this middle region here, bad things might happen, but this is still a fair amount of tolerance, and that's why we use digital circuits. So we've got this ability to reject the noise. Now let's take a look at an example here. Say I have a digital adder with no noise, and I'm going to do 0 plus 0 equals 0. So here are my two inputs, 0 and 0, and I'm getting an output, and well, we all know that 0 plus 0 is 0, so I expect a 0 volt output. Now let's see what happens when we add noise to that. So here's another digital adder. We've got our two 0 volt inputs, but now what happens is somebody across the room turns on their cell phone. And the radio signal from the cell phone hits the wires inside my computer. Those wires that were at 0 volts are now pushed up to 0.3 volts. And now what happens? Well, let's take a look at this transfer function over here. So how does this circuit here, it's a digital circuit, how does it interpret a value of 0.3? Well, a value of 0.3 is still interpreted as 0 here. So we're okay. Because we have this nice transfer function here, we're going to interpret both of these inputs as 0, and our digital adder is going to add up 0 and 0 and give us 0 volts out. And that's despite the fact that we had all this noise that changed these input values. So this is the benefit of having a digital circuit. Let's see what happens if we have an analog adder. So here's our analog adder. We have 0 volts in, but again we have this noise from our friend's cell phone, pushes these up to 0.3 volts, but the analog adder doesn't have this transfer function. So it's going to take 0.3 volts and 0.3 volts, add them together and give us 0.6 volts as the output, which is about 1. So the noise went right through the analog circuit. So this is why we like digital circuits. They're less sensitive to noise, which means we can put them together into bigger and bigger systems without the noise adding up. Now here's a question. What's the result of the following analog circuit where the inputs all have 0.3 volts of noise from a nearby antenna? Well, the output here is going to be 1.2 volts. You can look and see what happens. Here are 0 volt inputs, got our noise from our antenna, so we have 0.3 volts on all these inputs here. These are analog adders, so the noise goes right through them. So now we're going to get 0.6 volts out from each of those, and our next analog adder is now going to add 0.6 volts and 0.6 volts and give us 1.2 volts. So you can see very quickly that it's hard to build big circuits with analog components because the noise just keeps getting added up. Here's the opposite question. What's the result of the following circuit when we do the addition as a digital circuit? Well, it's going to be 0. So this time our noise comes in and all of our inputs get moved up to 0.3 volts, but we have that transfer function. So both of these adders are still going to interpret 0.3 volts as 0, add them together gives us 0 output, which is going to go into our last adder and give us a 0 as the output. So what we saw here is because these digital circuits are resistant to noise, we can build much larger, more complicated systems and still keep the noise out. So this is why we use ones and zeros in electronics today, because we have this noise resistance property, which means we can build big complicated things without the noise getting all the way through it.